Skin effect in electrical transmission. Introduction in electrical transmission systems, especially in high-frequency alternating current (AC) systems, the skin effect plays a crucial role in determining how current flows through a conductor. The skin effect is a phenomenon in which alternating current tends to flow predominantly on the surface of a conductor rather than uniformly throughout its cross-sectional area. This effect becomes more pronounced at higher frequencies, and it is essential to understand it when designing systems for high-frequency signals, power transmission, and electromagnetic interference (EMI) considerations. In this article, we will explore the skin effect in detail, covering its underlying physics, its mathematical description, the factors that influence its severity, its effects on the efficiency of electrical transmission, and practical implications for the design of electrical systems and conductors. Number 1. The physical basis of the skin effect. Number 1.1 Alternating current and electromagnetic fields. When a conductor carries alternating current, AC, it generates a time-varying magnetic field around it. According to Faraday's law of induction, this time-varying magnetic field induces circulating electric currents inside the conductor. These induced currents, known as eddy currents, oppose the flow of the original current according to Lenz's law, which states that the direction of induced currents will always oppose the change in magnetic flux that caused them. At low frequencies, the induced currents are relatively weak, and current tends to flow evenly across the entire cross-sectional area of the conductor. However, at higher frequencies, the changing magnetic fields induce stronger eddy currents within the conductor. These eddy currents create additional magnetic fields that oppose the original current flow, particularly in the center of the conductor. As a result, the current tends to concentrate more near the surface of the conductor, reducing the current density in the center. The phenomenon where the current is confined to the outer layers of the conductor is called the skin effect. Number 1.2 Electromagnetic wave propagation. To understand the skin effect more clearly, it's helpful to look at the interaction between alternating current and electromagnetic waves. At higher frequencies, the alternating current can be thought of as generating electromagnetic waves that propagate outward from the conductor. These waves induce currents on the surface of the conductor and are attenuated as they penetrate deeper into the material. At frequencies low enough for the depth of penetration to be large relative to the conductor's dimensions, the current is uniformly distributed. However, as the frequency increases, the depth of penetration decreases, and the current becomes more confined to the outer surface. The skin effect is a direct consequence of this behavior. Number 2. Mathematical description of the skin effect. Number 2.1 Skin depth, delta. The most important parameter when studying the skin effect is the skin depth, denoted as \delta \. The skin depth represents the distance from the surface of the conductor within which the current density falls to about 37% of its value at the surface. It is a measure of how deeply the alternating current can penetrate into the conductor before its intensity becomes negligible. The skin depth, \delta \, is given by the following formula: \delta equals \sqrt \brec2 \rho \mu \where \rho is the resistivity of the material in ohm meters. \mu is the permeability of the material in henries per meter. \mu equals \mu_0 times \mu_r where \mu_0 is the permeability of free space, and \mu_r is the relative permeability of the conductor material. \omega is the angular frequency of the current, in radians per second, given by \omega equals 2 pi f where f is the frequency of the AC signal in hertz. The skin depth equation shows that the skin depth is inversely proportional to the square root of the frequency. This means that as the frequency increases, the skin depth decreases, and the current flows more towards the surface of the conductor. Conversely, at low frequencies, the skin depth is larger, and the current is more evenly distributed across the entire cross-section of the conductor. Hash number 2.2 example of skin depth calculation. Let's assume we are using a copper conductor with a resistivity /ρ equals 1.68 times 10 to the power of minus 8 omega text m and the frequency of the current is 1 text megahertz First, we calculate the angular frequency omega omega equals 2 pi f equals 2 pi times 10 to the power of 6 text rad s equals 6.28 times 10 to the power of 6 text rad s next, we use the permeability of copper mu equals mu underscore 0 times mu underscore r where mu underscore 0 equals 4 pi times 10 to the power of minus 7 text h m and for copper, the relative permeability mu underscore r approx 1 Therefore, mu approx 4 pi times 10 to the power of minus 7 text h m substituting values into the skin depth formula delta equals sqrt frac 2 times 1.68 times 10 to the power of minus 8 4 pi times 10 to the power of minus 7 times 6.28 times 10 to the power of 6 approx 0.002 text m equals 2 text m thus. The skin depth for a 1 MHz signal in a copper conductor is approximately 2 mm. Hash number 3. Factors affecting the skin effect. Several factors influence the extent of the skin effect, with the most important being frequency, material properties, and conductor geometry. Hash number 3.1 Frequency of the alternating current. As noted earlier, the skin effect becomes more pronounced as the frequency of the alternating current increases. This is because the induced magnetic fields and the resulting eddy currents become stronger with higher frequencies, causing a greater concentration of current near the surface of the conductor. This behavior can be observed in high-frequency power transmission and signal transmission systems, such as radio frequencies, RF, and microwaves. Hash number 3.2 Electrical conductivity and resistivity. The skin depth is also influenced by the electrical resistivity of the conductor material. Materials with higher resistivity tend to have a smaller skin depth, meaning that the current will be more confined to the surface. For example, materials like copper and aluminium have relatively low resistivity and exhibit a larger skin depth compared to materials like iron or stainless steel, which have higher resistivity. Hash number 3.3 Conductor geometry. The shape and dimensions of the conductor can affect the skin effect. In general, smaller conductors will experience a more significant skin effect at a given frequency compared to larger conductors. Additionally, conductors with non-circular cross-sections, such as flat or rectangular conductors, can exhibit more complex skin effects, where the current distribution is influenced not only by the material and frequency but also by the geometry of the conductor. Hash number 4. Consequences of the skin effect. Hash number 4.1 Increased resistance. As the skin effect increases, the current density is confined to the surface of the conductor. This results in an effective reduction in the cross-sectional area through which current can flow, leading to an increase in the effective resistance of the conductor at high frequencies. This increase in resistance is due to the fact that current is flowing through a smaller volume of the conductor, and the surface area through which current flows is limited. The increased resistance can cause power losses in the transmission system, leading to inefficiencies, particularly in high-frequency power transmission, and in signal cables. Hash number 4.2 Heating. The increase in resistance due to the skin effect also leads to increased Joule heating in the conductor. As the current flows through the conductor, the resistive losses generate heat, which can cause the conductor to warm up. In power transmission systems, this can lead to higher temperatures and potential damage to cables and other components, necessitating more robust insulation and cooling solutions. Hash number 4.3 Impact on high-frequency signal transmission. For high-frequency signal transmission, the skin effect can have a significant impact on the signal integrity. In systems like radio frequency, RF, circuits, transmission lines, and antennas, the skin effect causes a loss of signal amplitude as the signal is confined to the surface of the conductor. This can lead to signal distortion, attenuation, and a decrease in the efficiency of the transmission system. In the design of such systems, engineers often use Litz wire, a type of wire made of many thin strands of wire that are insulated and twisted together, to reduce the skin effect. The Litz wire design helps by increasing the surface area through which the current flows and ensuring that the current is distributed more evenly across the conductor. Hash number 5. Mitigating the effects of the skin effect. Hash number 5.1 Increasing conductor size. One approach to mitigating the skin effect is to use larger conductors, which reduce the relative importance of the skin effect. In practical terms, however, increasing the size of conductors is not always feasible due to space constraints, weight considerations, and material costs. Hash number 5.2 Use of Litz wire. As mentioned earlier, Litz wire is a popular solution for mitigating the skin effect in high-frequency applications. By using many small, individually insulated strands, Litz wire increases the surface area available for current flow, reducing the overall effect of skinning. Hash number 5.3 High conductivity materials. Using material